everyone's attention. We'll do our last talk for lunch today, and they will be discussing quadratic prime generating polynomials over Gaussian integers.
I'm Monta Meirose.
And I'm Fuentes. And we're specifically going to be looking at a quadratic polynomial of the form ax squared plus bx plus c, where a, b, and c are integers. And what makes prime generating polynomials a little bit special is the fact that they generate many primes over an interval of values. And one of the most popular ones actually was discovered by Euler in 1772. And so on the surface, this one right here, x squared plus x plus 41, it may not seem very special, but it actually produces primes 86 times over an interval of x from 0 to 99. This is pretty cool. If you don't believe me, feel free to pull out some paper and pop in some numbers. But I'm going to continue while you do that. So we need a way to talk about how well these polynomials kind of output primes so well. So we're going to define an efficiency at doing so to be a percentage. And we're going to calculate that percentage to be the number of primes that are output over the total input values. And as you can see, this Euler polynomial has an efficiency of 86%, which is pretty cool. Now, so a question to ask is how do these polynomials do that thing they do? How do they generate primes so effectively? And to understand the answer to that question, we need to look at the coefficients a, b, and c and their relationship. And so we're going to use the quadratic formula, and we're specifically going to use that portion underneath the square root. So we're going to define a discriminant, d, to be b squared minus 4ac. And if we take a look at the discriminant of the Euler polynomial, we can see that it is negative 163, which is a prime number. So, this doesn't really tell us very much right away. So we're going to have to look at a couple more examples to really see what's going on. So we talked about this one, the Euler polynomial. So now let's go ahead and talk about this second one. X squared plus x minus 39. It looks very similar to the Euler one, but it only generates 23 primes for that same interval of x from 0 to 99. It's a little disappointing, but we look at its discriminant, we can see that it's also a prime number, 157. All right, so again, that one didn't really tell us a whole lot. It still kind of does, it outputs primes very much like the Euler polynomial, just not very well. But we're going to ignore that one right now, and we'll come back to it later. But let's look at number 3. And all these polynomials, really, we have one at the top, the good, the bad, and the ugly. And this one, unfortunately, is the ugly one. X squared plus x minus 42 generates absolutely no primes for the same interval of x from 0 to 99. But what's different about this one compared to the other two is if we look at the discriminant, we can see that it is 169, which is the squared number, 13 squared to be exact, and that means we can factor it. So if we take the quadratic formula, again, and we use it on this polynomial, we can see that it has roots at 6 and negative 7. So because this polynomial has a square discriminant, it can be factored down to x minus 6 times x plus 7. And because of this fact, no matter what number in that interval you plug in, all you're going to get out is composite numbers. So, that's pretty cool in and of itself, but, we didn't really do our research on composite generating polynomials. So, I have an idea that I want to look at this second one again. And, this might be a good idea, or it might crash and burn. But, we're going to do it anyway. So, before we can look at this particular polynomial, the second one, we need to understand modular arithmetic, because it's going to be important. Now, if you're not familiar with modular arithmetic, it's very, think of it like a clock system, and very much like the one over here. In a clock system, you count the hours by moving in a clockwise direction around, and when you get to 12, you're back at 0. So if we count up to 14 on this 12-hour clock, then we say 14 is congruent to 2 mod 12. And the only difference between 2 and 14 is a multiple of 12. So if we look at it, if we have an integer n, we say that it's going to be congruent to r modulo p if n minus r is a multiple of p. So if we look at this, oops, spoiler. So if we look at this one right here, 157, we can see that if we subtract 1, it's 156. 156 is a multiple of p, or 3. So therefore 157 is congruent to 1 mod 3. If we look at the first one, it's negative 163. So negative 163 minus 2 is negative 165. That's a multiple of 3. So, but to kind of see that, we have to, if we think of it using the clock again, if we count up to 165 in the opposite direction of the clock, we're going to land at 2. So, and the only difference between 2 and 165 is a multiple of 3. So, negative 163 is congruent to 2 mod 3. So, back to understanding what's going on with this polynomial. If we look at the residues, or residues is just another fancy word for remainders. If we look at the residues, we can see that it has 3, 0, 1, and 2. If we square these residues, and of course, squaring 2 is going to get 4, and so we've defined its congruency in mod 3, which is 1. Right away, we can see that, hey, 157 actually is a square. It's a square residue of mod 3, and it's 1. So what this means is we can do the same thing to this one that we just did to the other polynomial. We can factor it. Oops. We can factor it. And it factors down to x times x plus 1 in mod 3. So no matter what residue values you plug into it, 2 out of the 3 numbers are going to be divisible by 3. And that basically just means that this polynomial can only produce primes 1/3 of the time. So we just talked about 3 examples. One example was a polynomial that produces primes very effectively. A second example was a polynomial that produced primes a fraction of the time. And a third polynomial that really just embarrasses itself. So we need a way to kind of describe, since we're going to be looking for a lot of these polynomials, we need a way to describe whether or not a polynomial is even worth considering. So we're going to look, we found some work done by researchers Nigel Boston and Marshall Greenwood, and if we have a polynomial, quadratic polynomial, and it has, we say that it's going to be worthy of testing its efficiency if it meets these 2 criteria. So condition number 1 is a parity condition. A plus B needs to be even, and C needs to be odd. And the second one, the discriminant condition, is what we just talked about. The discriminant cannot be a square modulo of P for many small primes. So before we can apply this to our work in the Gaussian integers, we need to go over a few things first.
All right, so just some background on the Gaussian integers. First, the Gaussian integers live on a complex plane, as you can see in the picture, where the real axis is horizontal and the imaginary axis is vertical. A Gaussian integer, we'll call it alpha, has the form a plus bi, where both a and b are integers and I is the square root of -1. A conjugate of alpha is denoted by putting a line over the alpha, and it's essentially taking the opposite sign of your b value. So we were to graph it like this picture, alpha is for our a equals 2 and our b equals 1. We would have an alpha equals 2 plus I, and its conjugate would be 2 minus I. The norm of alpha, or when we say a norm of any Gaussian integer, is essentially the distance from 0 squared, which is of the form a squared plus b squared. There are 4 units in the Gaussian integers, plus or minus 1 and plus or minus I. So any given Gaussian integer has associates, which are plus or minus alpha or plus or minus I alpha. A Gaussian integer is even if it's divisible by 1 plus I, and it's odd otherwise. And a Gaussian integer alpha is prime if it is only divisible by the units or plus or minus itself. So when we were trying to adapt from integers to Gaussian integers, we actually found that Boston and Greenwood's work was essentially the same thing. We have the same conditions that we're calling worthy first, our first coefficient plus our second coefficient. Now we're calling them alpha and beta. We switched to Greek for the sake of using Gaussian integers. Must be even, and our third coefficient, gamma, is odd. And our discriminant is our beta squared minus 4 alpha gamma, is still not square mod small primes mu. But since we can't really order primes or really Gaussian integers, we decided to order them by essentially norms. So that way they were an equal distance from 0. And essentially the first condition guarantees that our polynomial will never be even, and the second condition guarantees that our polynomial is never a multiple of a bunch of small mu's. So we kind of put some of these, put these criteria in our computer, and we kind of got here 5 polynomials that we thought had a great efficiency, and we decided to pick these because they had similar discriminants, either they're associates or conjugate associates of the same discriminant.
So looking at these, I know it's going to be a little bit difficult to see any kind of relationship, but we're going to look at a couple of plots. I think it'll be a little bit easier, and we get to look at some color. So on the screen, we have 2 plots of 2 different polynomials. The colors represent inputs that if you put them into the polynomial, you're going to get a different output. So for the red, the blue squares, those are going to, if you put those into the polynomial, you're going to get prime outputs. The red squares are going to be composites, and the green squares are just going to be units. So go ahead and take a moment to look at these 2 plots and see if you can find any difference between the 2.
Does anybody have any ideas?
Shift it down on the right.
Correct. This plot on the right is the same as the one on the left, except shifted down by 3 units. All right, so let's go ahead and take a look at another one. And again, remember the blue squares are prime, red composite, green units. Go ahead and take another moment, see if you can find differences between these 2 plots.
Video?
Yeah, it's just twisted.
Yeah, actually, this one on the right is the same as the one on the left, except rotated 90 degrees clockwise to the right. So let's take a look at a couple more. I think you guys get the idea. I could ask you to take a look at and find differences between these 2, but that would be a little mean because it's a trick question, because they're identical plots. And that wasn't just because we used the same picture, we actually got the same plot for these obviously very different polynomials. Let's take a look at one more. Now, this one might be a little bit more difficult to see because it kind of looks like the second one, but if you take this plot on the left, you flip it over the horizontal axis, you're going to get the one on the right. So, obviously, as you can tell by now, these polynomials are all related. And here's the relation. So the one on the left was our main original polynomial, f of z. We got to the second one by translating it by 3i. We got the third one by pre-multiplying by I. And we got the fourth one by post-multiplying by I. If you remember, this was the one that had the exact same plot. And for the fourth one was really just taking the conjugate of the polynomial. And all that really means is if you take the conjugate of a polynomial, of one of these polynomials, you're just taking the conjugate of the Gaussian integer. So we have a theorem that we came up with that says, if you do form any of these operations on the polynomials, you're still going to maintain the worthiness of that polynomial, and they're also going to have the same efficiencies with one exception. If you translate by t, or if you pre-multiply by s, where t and s are just sum or any Gaussian integer, it's still going to be, the polynomial is still going to be worthy, but the efficiency may change.
All right, so we're actually going to switch gears here now, because after examining some of our polynomials, we noticed that they would have a really great efficiency, but we would have these sporadic or patterned red dots if we were to go back to the pictures. So we actually started looking at works by, or a paper by Mullen. And in the integers, he had created this definition that was essentially that any prime-generating polynomial had a prime production length, which was, if we started at 0, how far could we go out before we hit a composite? So for our first polynomial or our first example that we were talking about in the integers, x squared plus x plus 41, that actually had a prime production radius, or a prime production length of 40. Well, he was actually able to prove that there was a limit to that prime production length for certain polynomials, which actually we're going to call it Eulerian polynomial, which is of the form x squared plus x plus some prime a. This is for just in the regular integers. And if p is the least prime, for which the discriminant is square mod that p, then our prime production length is actually going to be less than that prime p. So we decided to actually take a look and see if we could maybe observe something similar in the Gaussian integers. So we came up with this definition. Essentially, we're considering our polynomial, and we're saying that our prime production radius, we're going to call it, is the largest norm for which all values of z with the norm of z are less than r produce prime outputs. And so if we look at our Eulerian form, and yes, we redefined pi. I didn't know it would be that important today. We are actually calling prime we're calling pi a prime Gaussian, any prime Gaussian. And we're saying that, okay, if we have a Gaussian polynomial of the form where both alpha and beta are 1, and our gamma is some sort of prime, we're going to call it pi, then our discriminant is going to be 1 minus 4 pi. And if we let our mu be the smallest prime for which our discriminant is square, then we're going to get at least 1, possibly 2 residues or 2 factored residues or 2 factors in each residue set, where a residue set is essentially the box created by our mu and our I mu, and then we centered it around our origin. And so since there are 4 multiples of mu that are still prime, essentially mu times the associates, then once we get 5 residue sets within that circle, there must be an associate, or there must be a multiple of mu that is composite. So here we drew out a circle that encompasses 5 full residue sets of mu. And then by using the Pythagorean theorem, we can see that the radius of our mu, using this triangle of units of 1/2 mu, we can find that our prime production radius must be less than 5/2 norm of mu. So this is kind of just capping off where our prime production radius can go. It doesn't mean that it's going to get our prime production radius is going to get close, it's just a max. So to kind of finalize, here we have 2 polynomials. They are both worthy. They both have a good efficiency, as we had. One is better than the other, clearly. But we also have our discriminants, where the discriminant of the first one is 41 minus 52i, and our second discriminant is 13 minus 40i. And the first mu, where the discriminant is has a square residue, is actually 1 plus 6i for the first one and 4 plus 5i. So not all of our polynomials are going to have this great prime production radius. I think in this one it's actually 1, because because when you try to factor out that discriminant, their factors are very far apart or very varied. And for our second one, because the discriminant factors are closer together, it actually creates this great prime production radius, which is 32, I believe. 32. Yeah. Had to rethink that. So, yes, we would like to thank everybody for listening.
Questions?
Why is it that translating gave you possibly changing the efficiency? Do you guys look at that at all?
Yeah, we did look at that. It has to do with, you go to,
Too far. This was the translated
Yeah.
one, the second one.
it's different, it changes because you're moving, while the polynomial, you know, it's still very similar to the first one. You're just kind of moving where those inputs are coming from, and you're going to put in numbers that just.
Yeah, so if you had like a polynomial that had, like in a lot of our examples, we had these, you'll notice like we have this great blob, which I'm pretty sure our prime production radius with this one is, somewhere, it's a good one. And then just by translating, you're moving it down. So then you're changing the efficiency because you've got more red up here. Then in theory, it gets more red as you go out.
Is it possible for there to be a small radius but a high efficiency?
Yeah, we actually had that for a couple times, just because it all depends on how you can factor the discriminant. So if our factors are like, if I was going in just the regular integer saying like, oh, we can factor this one out to 2 and 9, it's going to have a less prime production length than it would be if, say, we could factor it out to 4 and 5.
So yeah, you pointed out there's really big difference when you multiply like the inputs of the polynomial versus multiplying the outputs. Can you give an intuition to why there's such a big difference between those two?
I assume you're talking about
Yes.
essentially these translations. So, okay, you'll notice when he was talking about the factors that were the same, the only thing that we did between those was we pre-multiplied by a unit. So, okay, if you have something that's prime and you multiply it by 1 or I, it's still going to be prime. Now, if we're multiplying the whole thing by 3, no longer prime. A prime by 3 or anything. Multiplying a prime by another prime is going to give you something composite, so it's going to completely change if we pre-multiply, or if we post-multiply. If we pre-multiply, it kind of all depends on how that goes together with your third coefficient, because pre-multiplying only changes your first two coefficients and not your third.
We have one last question. I wanted to ask something. Do you guys feel good about what Greek letter you use for your
When we decided it, we're like, all right, we're using Gaussians. We have to go with, and we decided we're like, all right, Gaussians, Greek letters, all right, prime, P, let's use pi, okay. So
it seems fitting.
yeah, I mean, it was a whole logical thought process, and then we started talking about it today, like, we should have changed it.
Let's thank our speakers again.
So, quick note about lunch. We have lots of different types of boxes with sandwiches and chips and cookies in them. I would love for my vegetarians to go first. They're 10 Mediterranean veggie boxes. The drinks aren't super cold, so I'm going to put out some ice in case you want a cup with ice for your drink.
Also, just where to eat. I had mentioned before in an email that there's going to be some entertainment right outside at noon in Discovery Hall. There are lots of places to sit if you want to go out and sit in the sun a little bit, get out of the building. You're also welcome to stay inside the building. You can eat in here, you can eat out on the couches. But let's make sure that we're back here close to 1 o'clock for our next speakers.
How can I help?
Sure. I can make it this screen too.
Yeah, that's outside the screen.
This is my
And I told Cindy that yesterday, you see the program of tiling, discovery of how arts use the angles. Yeah, and then on the meters for this tiles, and very nice and beautiful. And
Oh,
was
pretty
on
cool.
there to talk yesterday.
She's actually
The story is that it should be up sometime this morning, so I haven't, I'm gonna check. But, anyway, it's kind of the thing that I keep on checking, which, you know, if you never make it to the news, right, you have to check this, right? So there was this Guardian and the number of shares on the article are crazy, really crazy numbers. So here, I'll tell you the most recent. They hear this morning.
Oh, yeah.
So you wrote this, are you?
I'm gonna grab my food and ultimately go outside, but I think I told her that we were gonna be outside too.
Excellent.
Okay.
And then the one that you got.
So, let's see.
Swim by and see where I'm at. Just to check, make sure. Or is this a hot or is this
Yeah, I think they, Lisa interviewed us. This came out of a project that we did with an undergraduate research student who has now graduated.
So he's not here.
So he works with us. He works in the area, he works for a startup, and,
Oh, sorry, is that your photo? Yeah, I'm sorry. You see him, yeah?
well, I can't find the most current number,
Just
but
walk off there.
this morning it's over 40,000 shares.
I mean, I have. Wow. Yeah, so I think we should,
Well, yes, 40,000.
should we?
That is great.
No,
So,
they'll probably have forgotten. We're gonna go over them anyways, but I don't have nothing to say.
for undergrad students, wanted, as long as somehow he made it to Wikipedia, he was fine, okay? And so that's one of the first things that happened.
So I ordered some extra lunches, so you're welcome.
Oh, thank you. That's very nice. Thank you.
Yeah.
I think I will.
Okay.
So,
Yeah, so, anyway, I'm
great.
gonna.
Well, go grab a.
Let's just keep them right
Okay.
Like to go through those now?
I don't really like anything.
So do you want me to? 'Cause I'm gonna go over there.
Okay.
Like
Thank you.
I still haven't eaten my ice cream yet, but you're tonight, right?
Okay. Good. Thank you.
Yeah.
I'm gonna grab lunch.
It's left in my backpack. I'll make sure.
Check on.
Press, actually, so.
What are we telling him?
Hmm? That he needs to not go to the last slide until after they ask us for questions.
Are we changing something?
I don't think so.
Oh, so we didn't need a table.
No. I'm realizing that now. This is really thick.
So, where'd you go?
I have no idea. He just disappeared. Whole hour.
Oh, cool.
So long.
Shunning the outdoors.
We thought we needed a table, but then we didn't actually need a table.
Well, we were considering changing something, but I don't think we're
We're gonna wait to do the question slide until after everyone applauds, because otherwise then it's, we ask for questions and then nobody answers them. And then, but we need to find Levi to tell him.
There he is! Levi! Levi!
And you, are you just shunning the day star?
Yeah.
So, I got this whole meal package here. They ran out of San Pellegrino before I got there.
What's that?
They ran out of this kind of stuff.
Oh. I mean, you can have mine if you want.
That's cool.
You get the ingredients.
Yeah, it's got a lot of food.
I'm gonna do alright.
Yep. I don't know, be okay.
Everybody else did pretty good.
I'm really nervous because like all of the Doppler groups were really good at presenting. Like, it seemed like they were just like exceptionally good presenters.
They did pretty good. We're pretty good though.
The first one was really confusing. I don't think I
I didn't follow anything.
I was confused like, right from the beginning.
Yeah, the first slide. I was like, I don't know what you're talking about.
And then you just kept going.
And now I got
Happening
worse.
to me.
But yeah. Also, let's not look at the screen.
It's gonna be hard.
I know, because what a few people were doing it.
Yeah.
The second bathroom
I like the presentation.
Yeah, it was interesting.
Very clear.
Yeah, it's very clear.
Cool topic.
The proof was a little confusing,
I'm gonna go read outside.
but they like made up
You're
for
really
it.
interested in drawing.
All the
It's
visuals.
like Steve said, like, it was really clear everything.
The hex type stuff and that.
Yeah, I really like that one.
You don't wanna go outside?
We were gonna, but then we were maybe gonna change our presentation, then we wanted a table, but now we're not gonna change it, but we're already here.
Well, that's fine. Lunch is good.
We go outside after you finish eating, so you don't think about other stuff.
What's the entertainment?
Dancing.
Is there a band?
No.
Is there a minstrel?
No.
There's someone carrying a ukulele down there. Next level. Here we go.
Oh,
What?
who else?
What?
It's so good.
No.
Yeah, it makes it crunchy.
Technology.
Technology. Yeah.
Makes it crunchy and better tasting.
I agree, you should try it.
Yeah. Thank you. I'll take your word for it.
I lost.
And then I'm not try the other half of tomato.
Too dry.
No. Much too wet. But it was also kind of like
Bland.
plain. Yeah. No, they put so much sauce on here. And listen, like the sauce doesn't taste bad, but I don't like how wet the bread gets.
What kind of sauce is it?
I don't know.
Is it like pesto mayo or something?
I don't know, yeah.
It's mayo?
Why?
Mayonnaise is so gross.
What?
You're eating it.
Yeah,
Good on
because I didn't know
sandwiches.
it was mayonnaise.
Dude, you,
Why
what the
did you
heck?
tell me that?
It's not mayo.
Thanks. Like, you guys don't know me at all, and we spent like 1 week together.
I didn't say it was mayo.
Levi.
I'm so confused.
Just eat it.
No, I'm afraid to.
You've already eaten half of it.
Yeah, but there's just a lot on here. I'm gonna scrape some off. I don't want to look at it while I'm eating it.
Close your eyes.
But I'd like to know what I'm eating. But now that I know, I don't want to look at it. It's
But what if
very-
he's wrong?
It's very complicated. I thought it was like hummus or something, but now I don't know. I mean,
Let
not
me
like
see
it
it.
doesn't
It's
taste
pesto
like
hummus.
hummus. Okay.
Yeah, that's exactly what it is.
You guys.
I don't know what it is.
Okay, I'm taking the tomato off. That's too much new stuff at one time. I can't handle that.
Tomato new stuff.
I don't like tomatoes, and this is stressing me.
Wait, stress her out.
Tomatoes have been in our cuisine for like 300 years.
Your cuisine. I don't eat tomatoes.
Did I say mine? I meant ours.
You
You
just
said
said
ours.
ours. That's why I said yours,
Oh.
not mine. It's really close. It's almost on the address.
I can make a better vegetarian sandwich
Yeah.
with avocado,
There should be avocado on this.
right?
Oh. It tastes different now that I know.
Tastes not bad. So much bread.
Bread's super good. It's got like, what's that crap
You
called?
have different bread than us?
Yeah, maybe.
We've got like tomato bread.
It's got like caraway in it.
Huh.
Really good.
I've never had banana before.
Me neither.
I like it. It's kind of expensive.
Yeah.
It's like 20% better than McDonald's.
What?
I mean, McDonald's is pretty disgusting. not like tasting, but like it's actually in all of their food is really gross.
Mhm. I agree.
Where's the safety waiver for the
She emailed it.
triplet, which, elevated sports?
Mhm.
Do I have to go to the website? Not found. Waiver. Got it.
Are they filming this?
Yeah, we don't have to watch it.
I never watched the last one. I just couldn't make myself do it. So I don't want to see it.
Yeah, I never watched that.
I think that's helpful.
Yeah.
It's just good to see what you look like.
Yeah.
You like pickles?
Me?
Yeah.
Yeah.
You want my pickles?
Yeah.
You don't mind?
I don't know if I can handle the pickle.
You guys didn't get one?
I got one.
It's like a little pickle strip. It's not a whole one.
Pickles like Coco's?
Just
Here,
why
you
would
can
you
have
ruin
this, I
a
don't want it.
cucumber like that?
Yeah, Daisy.
So why would you ruin cucumber like that?
Yeah, for
What?
one I didn't even know it was.
What?
Pickles, they're disgusting. And they would be better if they were not
You
pickled.
need to stop talking about food.
They're just too different.
Remember if I turned the video camera off?
Oh boy.
I did not.
Okay.
Enjoy our
So-
conversation.